Hi guys, uh, welcome to the second part of this lecture. In the first part, uh, we have got a brief overview of IOP, and in the second part, we will try to explore how the concept of IOP has been implemented in different computer architectures. So, just a quick recap. What was the basis of IOP implementation? The basis of IOP implementation is try to execute different instructions parallelly at the same stage of pipelining during the same clock cycle whenever possible. Just go back to the example. Try to execute different instructions parallelly in the same stage of pipelining in the same clock cycle whenever possible. This was the basis of um, instruction level parallelism, and in this part we will study different architectures which have implemented this IOP concept. First one is super pipelined architecture. So in super pipelined architecture, what usually is being done is super pipelining is the breaking of stages of a given pipeline into smaller stages, thus making the pipeline deeper. So in super pipelining, what usually being done is, say, this is your entire process. So in pipelining, what you usually do is usually divide a task into smaller subtasks. So this is your instruction fetch. This is your sorry. This is your instruction decode. This is your fetch operand. This is execute, and this is your write back. This was the concept of pipelining in SISD architecture. Now, in super pipelining, what you have to do, just try to divide a stage into smaller substages. Try to divide a stage into smaller substages. Say instruction fetch. Try to split this instruction fetch into two substages. By doing this, what will happen? Actually, what happens here is that not all pipeline stages need the same amount of time. For example, instruction decoding is faster than other stages such as fetches and store or write back. So what you have to do is just you have to use an internal clock. Internal clock where? Internal clock into the stage itself. And this internal clock will be faster, typically double than the external or universal clock. Thus, what will happen in the same clock cycle? We can overlap two subtasks or two different instructions. Just come to this diagram. The top one is your pipelining. Here you can see that in a clock cycle, just one stage, just one operation in a stage takes place. For example, in the first clock cycle, you have instruction fetch. In the second clock cycle, you have instruction decode, instruction fetch. Two stages are running parallelly. This was the inherent concept of pipelining. But in super pipelining, if you look into this portion of the diagram, you can see that instruction fetch stage basically overlaps with another instruction fetch. And how this has been achieved, if you go back to the previous description, instruction decoding is faster than other stages such as fetches and stores. So you have employed an internal clock which is faster than the external universal clock. So if somehow the instruction fetch for the previous instruction is complete by this time, then you try to fetch another instruction in the same clock cycle. Super pipelining. Pipelining inside pipelining. Now come to the next concept. Superscalar architecture. Superscalar architecture does what? A superscalar processor is one that can fetch, execute, complete more than one instruction in parallel. So this has been achieved by using some extra bit of hardware. If you go back to the previous diagram, the diagram for generalized pipelining concept, you have one segment for instruction fetch, one segment for instruction decode, one segment for execute, one segment for memory operations, one segment for write back in your processor. So at a clock cycle, only one instruction can access a particular segment. Now what will happen if we employ more than one instruction fetch segment, more than one instruction decode segment, and so on? This is the idea behind superscalar architecture. If you look into this diagram, in this virtual scenario, you have 4 segments for instruction fetch, 4 segments for instruction decode, 4 segments for instruction issue, 4 segments for execution, and 4 segments for write back operation into your processor. So if the instructions can take the advantage of instruction level parallelism, for example, if the instructions are something like this, then you can employ this superscalar architecture to achieve some extra degree of parallelism. For example, you can fetch A0, A1, A2 and A3 parallelly. Then once those 4 instructions are fetched, they will be passed to decode segments together. Now you can fetch 4 more instructions parallelly. And this entire architecture is possible because of this instruction level parallelism or loop unrolling phenomenon. Last one. Next comes VLIW architecture, very large instruction word architecture. In very large instruction word architecture, basically number of instructions reduced by merging more than one instruction into a single instruction. Just come to this diagram. This is basically a very large instruction word example. What happens here is you are embedding a load store type instruction, floating point add type instruction, floating point multiply, one branch, one integer arithmetic, when these instructions are independent of one another into a single instruction by using a very large instruction word compiler. So this is another example of compiler level parallelism. Now pass this entire instruction as a whole to your VLIW processor, where you have different segments for different operations which have been embedded into VLIW instruction. Say for load store you have a segment, for FP add you have a segment, for integer arithmetic you have a segment, for branch you have another segment into a single processor. Last, here you have a block diagram for a typical VLIW processor. See, these are your VLIW instructions and these are your functional units. Functional units are generic names for these different types of units. Depending on the type of computation your processor is going to perform, you will add different types of functional units into your processor. So this was the idea and implementation guidelines behind instruction level parallelism. Now your task will be to study this note carefully. After studying it roughly, then go to the video lectures. After carefully watching the video lectures along with the note, then again read the notes carefully. And another thing is that after this module is complete, that means when we are done with this array and vector processors, then I will issue some assignments to you which you have to submit to my email. So thank you and give it some time. Good luck.